So this is 1997, number 1 for your response. So it says here that a 0.2 kilogram object, so that's probably important, moves along in a straight line. The net force acting on the object varies with the object displacement as shown in the graph above. The object starts from rest, so that is really important, at displacement x equals 0 and at time t equals 0 and is displaced a distance of 20 meters. It shows that up here. Determine each of the following. So the first part, the acceleration of the particle when its displacement is 6 meters. Well, at 6 meters, we can see here that the force is 4 newtons. Newton's second law tells us that the sum of the forces on an object is its mass times acceleration. Or you can just start off with this. Acceleration is force over mass there. We only have one force, as far as we know, that one right there. So we can simply plug in. We've got 4 newtons of force, and we've got 0.2 kilograms there. So that winds up being 20 meters per second squared would be the acceleration. And that's it. So it's so easy that some people think it's harder than that and they wind up making it take more time. So the next part says the time taken for the object to be displaced the first 12 meters. So now let's do a kinematic problem here. We know that our initial velocity is 0. We know that we're looking for the time. We know that our displacement here is 12 meters, and we know that our acceleration is 20 meters per second squared. So what kinematic equation involves all 4 of those? It is the third one. So delta x equals v0t plus 1/2 at squared. There is no initial velocity. So I'm going to do 2 things at once. I'm going to solve for the time and cancel that out. So multiply a 2 times the delta x, divide by the a, take the square root. Hopefully you've got that as a fairly memorized equation. Lots of times we use it for dropping in an object, so that's g and delta y, but it comes from the same place. So now let's plug in here. We've got 2 times our displacement is 12 meters, and our acceleration is 20 meters. So our acceleration there should be 24 over 20, square root of that, and I think it works out to be about 1.09-ish seconds. All right, next part. Determine the amount of work done by the net force displacing the object the first 12 meters. So that is contained in this area. The work is force times distance, and that is contained in this area here, because here's the force up here, and here's the distance this way. So it's the area underneath this line here that will give us that. So we can simply see here that that is 4 newtons times 12 meters, and that is 48 joules of work being done there. Next part, find the speed of the object after it's been displaced 12 meters. So I'll show you a couple different ways that you can do this one. The first one, which we might as well start with to get some practice with it, is the work energy theorem. It states that the work we do goes into changing the kinetic energy of it, right? So this is really final kinetic energy minus initial kinetic energy. But it started from rest, so it had no initial kinetic energy. So that being said, since we know the work done, we just solved for it. We did 48 joules of work. That means we changed the kinetic energy by 48 joules. That means the final kinetic energy must be equal to 48 joules. And we can set that equal to 1/2 mv squared. So 48 is equal to 1/2. The mass is 0.2, and we'll solve for the velocity squared there. So when you work that out, you will get that the velocity is roughly equal to 21.9 meters per second. There's a completely different way you can solve it with kinematics. And if this question came up on the test, either way would be considered valid unless they said solve it with work energy theorem and with kinematics. So another one we could also do, because we already have the time at 12 meters, is we could use the first kinematic equation. So the final velocity is equal to the initial velocity plus the acceleration times the time. There is no initial velocity, so the final velocity is equal to the acceleration, which is 20. Multiply that by the time, which we already solved for in part C, which is 1.09, and if you multiply those two together, you'll get 21.9 meters per second. Same thing. So now it says find the final speed after it's been displaced 20 meters. So this is pretty similar here. We already found that this area here is 48 joules because of the force times the distance here. Now we got to do the same thing, find the area here. So this one is going to be a triangle, so it's 1/2 base times height. And so the area of this will be 1/2. The base goes from 12 to 20, so it's 8, and the height is 4. So 4 times 8 is 32. Half of 32 is 16. So the area there is 16. Now we can treat it the same as here, and we could begin our problem here and say, oh, we got a certain amount of initial kinetic energy, but I think it's easier just to completely start this over here. So if we look at our total amount of work done, 48 joules here, 16 joules here, so that's a total of 64 joules of work done. So let's do the same thing here. We know the work is equal to the change in kinetic energy, which is equal to the final kinetic energy because we started from rest. So now we can say this, that 64 joules of work is equal to our final kinetic energy, which is 1/2 times mass times velocity squared. So 64 is equal to 1/2 times 0.2 times v squared. And finally solve for v. I forgot to do that beforehand. So 64 divided by 0.5 divided by 0.2. Take the square root of that and, whoops. Give me a second here. You get about 25.3 meters per second. That makes sense. It should be a little bit more than 21.9 because we pushed on it for a little bit more of a distance there. Last part here, we almost certainly haven't talked about in class yet since we cover energy before momentum, but I'll go ahead and solve it. In this case, the change in momentum of the object as it's displaced from 12 meters to 20 meters. So from here to here. So the change in momentum will be defined as the mass times the change in velocity. So we can go ahead and solve for this. The mass is 0.2, and our change in velocity is we want from 21.9 meters per second to 25.3 meters per second. So 25.3 versus 21.9 means we've changed our velocity by 3.4 meters per second. So 3.4 is our change in velocity times our mass, and we get 0.68 kilogram meters per second is our change in momentum. We probably haven't covered that yet, but in case we're doing this problem later in the year as a review, that's how you solve that one.